Hello, it's Bill Manuel again, here to talk about gravity. And this time we're going to discuss how gravity behaves as far as entropy in the entire universe. Every measurement of gravity locally affects the size and shape of the universe. So here's how it goes. On my previous videos, we discussed how gravity is projected from the cosmic event horizon, and the cosmic event horizon accumulates gravity when objects go across it relative to us. When we see a galaxy cross our cosmic event horizon, all the quantum information that crosses is encoded as negative energy, which is gravity. And it's encoded by one quantum bit of information per Planck area. So the gravity is per Planck area of this cosmic horizon. And that cosmic horizon causes the relative gravity that causes dark energy. So here's how it works. This energy pool gets filled with objects crossing our horizon. And when it projects a gravity bit from the cosmic horizon down to locally, the cosmic horizon gets one Planck area smaller. It uses that bit so that A and B can correlate their spins, and the cosmic horizon gets a little bit smaller, which means it becomes a little bit closer, which means that the value of dark energy rises a little bit. So to counteract this, to conserve the energy of the system, after the gravity bit is emitted down locally to a black hole or anywhere where there's gravity, then nature takes that second particle and the cosmic horizon potentiates a Hawking radiation photon. So the cosmic horizon gets a little bit smaller, and now the universe is smaller. But to compensate, the universe is going to produce one Hawking unit of radiation, so the total energy of the universe is conserved. So this is how everything that happens via gravity here actually changes the structure and the shape and the value of dark energy on these distant horizons. And one other to think about is black holes are extremely energetic objects. A lot of scientists like to think they're cold and just voids, that's all. But they're not. They interact at extremely high speeds. We've shown how they produce 10 to the 46 joules of Hawking radiation, 1900 times a second for a 1 kilometer black hole. To give you some perspective on that 10 to the 46 joules, type 1a supernova is only 10 to the 44 joules. So that 1 kilometer black hole is emitting more radiation than a type 1a supernova, 100 times the radiation, 1900 times per second. But these photons are very low energy. They're 10 to the negative 30 joules. Background photons, just from the cosmic microwave background, they're at 10 to the negative 23 joules, so 10 million times bigger. So that's why we're probably not going to even be able to see that Hawking radiation. There's a huge number of photons, but detecting any one single photon is very difficult with wavelengths that low. But what we found was there's a critical speed that particles assume on any event horizon. And that speed I've called velocity critical, or V critical, is 1 minus 1 divided by the number of Planck areas times c. And that gives you like 99.9999 out to 37 decimal places, or 38, and then some number of c. So when I use this number and I calculate the time dilation from special relativity, I get 10 to the 19 in time dilation. So then I take, what would the time dilation be at 1 kilometer on the surface of the black hole according to general relativity? 10 to the 19. So general relativity and special relativity, they join together at the surface of a black hole. And I'm saying that black holes are very energetic. And you can tell because the particle speed time dilation is exactly the same as the gravitational time dilation. And just the way of how energetic things are, and also to conserve energy and information, gravity is an emission process. So far, people have not looked at the cost of measurement energies And that's why people have not found gravity yet. They think, oh, those little tiny energies in Landauer limit are so small, they just don't matter. They do matter. They're the exact same smallness as gravity. So this is gravity, folks. And we talked about how this satisfies entropy of the entire universe. That our gravity that we get emitted locally is dependent on the gravity bank of the holographic horizon. And when that gravity bank runs out, dark energy is going to be extremely high because the cosmic horizon will be very close because there's not that many Planck areas left. And it's going to be a very small and energetic universe. Well, anyway, thanks for listening. Watch my other videos. Look at the descriptions. I got some math in there too. I've got some papers put out. William Manuel, Open Science, got a paper out there. So this is it. And people that watch this, you're going to be able to understand gravity before all the talking heads in academia, all the famous physicists and Sabine and all the YouTube promoters. They don't know this yet. You do. You're in a very elite group of people right now, or very small group at least, a very small group of people that actually understand how gravity works, while the people who purport to know everything, they haven't got it yet. I'm trying to break through, but hopefully with your guys' help, we can get this out there, because this could lead to gravity tech that will totally revolutionize everything in humanity. But just can we get humanity to listen? I don't know. It's going to be a roll of the dice. Have a great day, and we'll talk to you later. Bye.